Let's practice finding rational zeros of polynomials together. For number 1, we have our polynomial function here of f of x is equal to x cubed minus 8x squared plus 11x plus 20. First, to get started, let's start by listing out the possible rational zeros. To get started, there are two important numbers to remember. One of them is going to be p. Now, p is going to be all the factors of our constant term here. So in this case, for p, we're going to have plus or minus 20 here. Okay. And besides p, we have one more variable right now we need is q. Q is going to be all the factors of the leading coefficient. So the leading coefficient here is 1. So we're going to have plus or minus 1, or all the factors of plus or minus 1 be what q represents. So remember that all the possible rational zeros that this polynomial could have has to come from the ratio of the factors of p to the factors of q here. So for all the integer factors of p, which is plus or minus 20, we could have p be plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 5, plus or minus 10, and plus or minus 20. Now for q, q is a little bit simpler, right? So q just had 1, so we're just going to have plus or minus 1. Now, taking all these integer factors of p and dividing them by all the integer factors of q, let's create a list of all the possible rational zeros. Dividing each of these p-values by a positive one or a negative one, our list is going to consist of possibly plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 5, plus or minus 10, and plus or minus 20. If q is another number besides 1, we would have more work to do, but in this case, it's essentially just all the factors of p this time. Now that we have a list of 12 different possible rational zeros, let's go ahead and use synthetic division to test them out to see which one may be a rational zero. Alright, so try not to overthink this part too much, just choose one of your numbers and get started. I'm going to start with 1, and then write my coefficients down for my polynomial. So we had a leading coefficient of 1, there was a negative 8, a positive 11, and a 20. Alright, so this process is a little bit tedious, but again, it's not too difficult. We just have to give it a try. So let's bring this 1 straight down. This 1 times 1 is going to be 1. Negative 8 plus 1 is negative 7. 1 times negative 7 is negative 7. 11 plus negative 7 is 4. 1 times 4 is 4. And 20 plus 4 is equal to 24. So notice that's not equal to 0, which means that 1 isn't going to be one of our rational zeros. Again, try not to get too stuck on this part, just move on to another number. I know there's a lot to try, but more often than not, it's not going to take you all of the tries, right? So let's do 1 and then negative 8, 11, and 20. Let's go ahead and try this again, but now using x equals negative 1. Alright, let's get started with just bringing down this 1, and so we have 1 times negative 1, which is negative 1. Negative 8 plus negative 1 is negative 9. Negative 1 times negative 9 is positive 9. 11 plus 9 is 20. Negative 1 times 20 is negative 20, and then negative 20 plus 20 is equal to 0. So this actually works out really nicely for us, which means that because we had a remainder of 0, that this x equals negative 1 is a rational zero for this function. Alrighty, now that we have one of our zeros, let's go ahead and factor. So just to be super clear, remember what our original polynomial was, right? We had f of x was equal to x to the third power minus 8x to the second power, and then we had plus 11x and then plus 20. Right? So this was the original polynomial that we had. It was cubic. And what did we just figure out right now? Well, what we just figured out is that when we did polynomial long division, we found out that x equals negative 1 was one of the zeros. So what that tells us right away is that x plus 1 is going to be one of our linear factors or binomials here. Okay, that's what the negative 1 tells us. Negative 1 would make that binomial equal to 0. And as for this 1, negative 9, and 20, we can go ahead and use those and create a trinomial factor here. So that's going to be 1x squared minus 9x, and then plus 20. Now, while this is a linear factor, which can't be simplified, here we have a quadratic factor, which can potentially be. So we should try to factor this, okay? So off on the side here, we're gonna do coefficients of x squared, I'm just gonna say are going to be x and x, right? So 1x and 1x. And then we have factors of 20 that are gonna add to -9, since a is 1, this is kind of nice. So I'm gonna use -4 and -5. So if you multiply across here, that would be -4x, this would be -5x, those combine to make -20x. So let's go ahead and just copy down that first linear factor that can't be simplified, this x plus 1. And then in terms of this quadratic here, we're going to get two binomials. One's going to be the quantity of x minus 4, and the other one's going to be the quantity of x minus 5. This would be our completely factored form for this cubic polynomial. So again, when we look at these three linear factors, they can help us with our zeros. So what makes each of these become 0? One would be -1. A second one here would be x equals +4. Basically what makes each of those binomials equal 0. And then x is equal to +5. If you wanted to write them as ordered pairs for the x-intercepts, you can do that too. So -1, 0. We could also say 4, 0. And then finally we can say 5, 0. So in case it's helpful to kind of tie in some more ideas here, if we want to make a rough sketch, this should be pretty doable. We know this is an odd polynomial, so we hopefully know what the end behaviors are going to look like. I'm going to show that in just a moment. And we also have a positive leading coefficient, so that tells us a little bit about what this graph could look like as well. So for the end behavior, we first have as x is approaching -infinity, or as the graph goes to the left forever, what's happening to these odd degree polynomials? Well, f of x is going to be approaching -infinity as well. I'll show this in just a moment. And as we move to the right, or as x approaches +infinity, right, we should be able to say here that f of x, or the y values, is going to approach +infinity as well. A couple other key features here, because this polynomial is in standard form. This 20 lets us know that we're going to have an intercept on the y-axis at 20. So if I go ahead and put a point at 20, let's call that 20 up here. That's a rough sketch. Okay, and then we have these three zeros. So we have this -1, 4, and 5. So those are all x-intercepts. So this isn't completely drawn to scale, I'm aware, but here maybe it could be -1. And then we could say +4 would be somewhere over here in the positive x-axis. And then 5 would be somewhere pretty close to the right of that 4. All right, so let's go ahead and see if we can make a rough sketch here. So we know we're coming down to the left because of our end behavior, right? As we go down, as we must be going to the left as well. We go through the y-intercept of this 20. We got to come through this x equals 4, and then also come through this x equals 5. And then this has got to be rising to the right as we go up forever. So this would be a rough sketch of this cubic polynomial. Let's check out one more. This one's going to be a little bit more work though. For number 2, we have this polynomial function f of x is equal to 10x to the 4th minus 11x cubed minus 42x squared plus 7x plus 12. Let's start with our possible rational zeros. Okay, if you want to pause and try this on your own, feel free to do so as well here. But it looks like that p is going to be this positive 12, so we're going to have all the factors of plus or minus 12. And then we also have to figure out what q is. Now q looks like it's not as nice as the last problem. Q is going to equal 10, so we're going to have plus or minus 10, all the factors of that. So let's go ahead and see the possible rational zeros x could equal are going to be the ratio of all the factors of p to q. At least that's going to create our list of possible ones, and then we're going to choose from there which ones to try. So let's go ahead and write out all the factors of plus or minus 12 for p. So we have plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, and plus or minus 12. So those are all the factors for p. And then for q, last time we just had 1, but q here is 10, so we have plus or minus 1, plus or minus 2, plus or minus 5, and then plus or minus 10. All right, this next part is going to be a little bit more work here, so let's go ahead and see if we can do this piece by piece. So let's go ahead and take all these factors of p and then divide them by q first, but when you divide anything by 1, they're all going to stay the same. So I'm just going to go ahead and copy down all these first ones. So we have 1, 2, 3, 4, 6, and 12. So that's going to take care of dividing all the factors of p by at least 1 for q. So now let's go ahead and work with this 2 for the q values, right? So let's take all of these factors of p and then divide them by 2. So let's see, 1 over 2, that's going to be a new one because that's half. That's not on our list right now. So we can write plus or minus 1 half. And let's go ahead and now do 2 over 2. 2 over 2 is just 1, so we don't have to deal with that one. Let's do 3 over 2. That's a new one. So any fractions right now are going to be new. So plus or minus 3 over 2. Okay. Now let's go ahead and do plus or minus 4 over 2. But 4 over 2 is just equal to 2, which we already have on our list. Let's do then 6 over 2. That's going to be 3, which we already have on our list. And then 12 over 2 is equal to 6, which we already have as well. Okay. Let's move on to plus or minus 5. Okay, so we have 1 over 5. That's a new fraction here. So we can write plus or minus 1/5. And then we can move over to 2 over 5. That's also a new fraction here. So we can go ahead and write plus or minus 2/5 here. After plus or minus 2/5, we can go over to 3/5. Let's go ahead and add that to the list. Plus or minus 3 over 5. After that, we have plus or minus 4 over 5. Plus or minus 4 over 5. These are tedious, I know. Then we have, 6 over 5? That's another new fraction, unfortunately. Plus or minus 6 over 5. And then we have, 12 over 5. Alrighty, that was a lot of new ones. Plus or minus 12 over 5. All right, finally on to the last q value of 10. Okay, so let's go ahead and do 1 over 10. Start with that, plus or minus 1/10. Then move on to 2 over 10. Now 2 over 10 is the same thing as 1 over 5, which we already have, so let's skip it. Then we have 3 over 10. I think that one's new. So plus or minus 3 over 10. And then we have 4 over 10, but 4 over 10 is 2/5, which we already have. We can skip it. 6 over 10 is the same thing as 3 over 5. We can skip it. And then 12 over 10 is the same thing as 6 over 5, so we can skip that. So this is going to be our entire list of possible rational zeros for this quartic polynomial. All right, so we have a long list of possible rational zeros. Let's just start testing some. I'm going to start with some whole numbers here, and if I have no luck with some whole numbers, I may switch over to some smaller fractions and then try those out as well. We have a few different options to try out here. So I'm going to start with 1 and then work my way from there. So this is just going to take a little bit of practice. Feel free to pause and try some of these on your own though, just to get some practice in. So we have 1, I'm going to try, right? And then let's see, I'm going to write my coefficients down. So we have 10, negative 11, negative 42, 7, and 12. All right, so bringing this 10 straight down here, 10 times 1 is going to be 10. Negative 11 plus 10 is going to be negative 1. 1 times negative 1 is negative 1. Negative 42 plus negative 1. Negative 43, this will be a negative 43 as well. 7 and minus 43, that should be negative 36. Negative 36 goes up here as well, and then negative 24. So that's not what we wanted. So 1 is definitely not one of our rational zeros. Now let's go ahead and just try maybe negative 1 here, see how that goes. So if we plug in negative 1, this 10, let's go ahead and just repeat the process here. That's 10, that's negative 10, negative 21, positive 21, negative 21 again, positive 21, 28, negative 28, and then looks like we have negative 16 here. So again, not one of our zeros, but looks like we're getting closer to 0. All right, so we tested 1 and we got negative 24 out. We tested negative 1 and we got negative 16, which is closer to 0. I'm going to try a smaller number now and see if we can get even closer. So let's maybe try something like negative 2, okay? And let's go ahead and bring this down. So this 10 is going to come straight down. Negative 2 times 10 is negative 20. Negative 11 plus negative 20 is negative 31. Negative 2 times negative 31 is positive 62. Negative 42 plus 62 is positive 20. Negative 2 times 20 is negative 40. 7 minus 40 is negative 33. Let's see, negative 2 times negative 33 is positive 66. And then 12 plus 66 is 78, so that did not work at all. Bring down this 10 to begin with. I know fractions aren't the nicest, but we do negative 3 halves times 10. I think that's going to cross cancel. We'll have negative 15. Negative 11 plus negative 15 is negative 26. And then negative 26 times negative 3 halves, cross canceling, we'll get 13 times 3 is 39, and it's going to be a positive 39. Negative 42 plus 39 is going to be negative 3. And then negative 3 halves times negative 3, unfortunately, no cross canceling. That's going to be positive 9 over 2. Positive 9 over 2. Or actually, instead of 9 over 2, we could write maybe, 4.5. Might be a little bit easier, I'm not sure. Adding 7 plus 4.5, that's going to be 11.5. I'm going to keep that as an improper fraction just because we had to multiply here. This is 23 halves, or again, that's 11.5. And then multiplying negative 3 over 2 times 23 over 2, that's going to be negative 69 over 4. Negative 69 over 4. Interesting, so we have 12. 12 is 48 fourths. 48 fourths, take away 69 fourths. That should be negative 21 fourths. Negative 21 over 4, which is the same thing as negative 5.25, right? Okay, so that didn't give us 0, unfortunately, but if we're trying to see what's happening here, it looks like this is the closest value we have to 0. So we're getting closer. I think we should maybe try another fraction and maybe keep it a negative fraction. So let's go ahead and maybe try something not too bad. I'd rather try easier things than more messy ones. So let's try a negative 1/2 here. So let's go ahead and give this negative 1/2 a try. All right, so snagging this negative 1/2, let's go ahead and try this out and see if that gets us any closer to 0 or exactly 0. That would be nice. Let's take this 10 and bring it straight down. Half of 10 is 5, so this is going to be a negative 5. Negative 11 plus negative 5 is going to be negative 16. We like even numbers here. 16, half of that is 8, so we have a positive 8. Negative 42 plus 8 is going to be a negative 34. Half of 34 is 17, so we're going to have positive 17. 7 plus 17 is 24. Ooh, half of 24 is 12. It's a negative 12, and we finally have a 0. All right, awesome. All right, so since this negative 1/2 did work, we know that we have a binomial here of, we can go ahead and write this as f of x is going to be equal to, and then we have basically x plus 1/2, right? Because negative 1/2 makes it become 0, so that's one of our factors right now, okay? Now remember, this will be a constant, this will be linear, this is quadratic, so this must be cubic. So using those coefficients, we can say that this would be 10x to the third power minus 16x to the second power minus 34x, and then plus 24. So at this point, we do have one of our factors, but we are looking for potentially 3 more. So we have this cubic polynomial over here, and we're going to see if we can find out the other 3 zeros here. Okay, so let's move up a little bit here, and let's go back to finding our possible rational zeros again. This time, we're just going to be using this cubic polynomial, though, so it should have less options. Now, before we take all of our factors of p and divide by factors of q, which we're going to have a lot here, notice how each of these terms have a GCF of 2. We could actually factor out a 2 so that we have less options to deal with here. So if we want to, we can go ahead and factor out a 2 and say this will be f of x, right, is equal to, and put a 2 out in front here and have the 2 be here and say that's going to be times this x plus 1 half factor, and then just take half of all of these ones. So we would have here 5x to the third power minus 8x to the second power minus 17x, and then plus 12. So at least 5 is a prime number, has less factors, and 12's also got less factors than 24. So if we want to now go ahead and use this 12 for P and then this 5 for Q, that should save us a little bit of work, right? So for P, we have plus or minus 1, 2, 3, 4, 6, and 12. Okay, and then for Q, this one shortened the list a bit, right? That's going to just be plus or minus 1 and plus or minus 5. Now if we go ahead and divide all of our P factors by our Q factors, let's start by dividing everything by 1. That's all going to stay the same, so we have plus or minus 1, 2, 3, 4, 6, and 12. And now dividing everything by 5, it looks like those are all going to be new because they're all fractions, right? So 1 over 5, 2 over 5, 3 over 5, 4 over 5, 6 over 5, and 12 over 5. All right, now what is our next step? Well, we have our possible rational zeros. Let's go ahead and see if we can then test some zeros using synthetic division. All right, let's give it a go. All right, so let's go ahead and just maybe pick one to start with here. I'm gonna maybe stay away from whole numbers and maybe try some fractions here to begin with. Maybe try something like 2/5 and see what happens here. We do 2/5. Let's go ahead and bring down this 5. 5 will cross cancel with that 2/5 to get 2. 2 times 2/5, that's going to be 4/5. This is interesting. This is going to be negative 7 and 1/5. Okay, 7 and 1/5 is going to be the same thing as 36/5. Now, negative 36/5 times 2/5 is negative 72. Let's see, negative 72 over... Let's see, negative 72 over 25. And if we keep going here, this looks like it's going to be pretty messy. So maybe I'm going to stay away from 2/5. Let's just back up real quick. Let's delete all of this stuff. And let's maybe try 1/5 while we're at it. See if this is any better. If we do 1/5, this 5 comes straight down. 1/5 times 5 is going to be 5. Negative 8 plus 5. So far, this is a little nicer. Negative 3. This would be negative 3/5. And then this kind of starts falling apart again. So this is negative, let's see, that's negative 17 and 3/5. So I guess what are we asking here? Will this multiply to get to negative 12? If it doesn't, then that doesn't make sense either. So, all right, so we tried 1/5 and 2/5. I'm just trying 3/5 now, another positive one. If it doesn't work, maybe I'll try some negatives. But again, why not just try positives first and then make arrangements after that? So let's bring this 5 straight down. 3/5 times 5 is going to be 3. Negative 8 plus 3 is going to be negative 5. 3/5 times negative 5, it's going to cross cancel. We'll get negative 3 here. Negative 17 plus negative 3. Oh, this is really nice. This got to be working, right? That's also going to cross cancel with the 5. That's going to be, oh, it's going to be negative 12. All right, perfect. 12 plus negative 12 is 0 here. So we have finally found what we are looking for. So this 3/5 does tell us one of our zeros. So remember earlier we found out that this x plus 1/2 was one of our factors, and that was because the negative 1/2 worked. Well, now that we see this 3/5 working here, we now know another 0 as well, or another factor. So from this, knowing that this is 3/5 is going to work, then we know one of our factors is going to be x minus 3/5. Okay, that's what we're just finding out from what we just did. And then these values at the bottom can help us with our trinomial here. So again, this is going to be 5x squared minus 5x minus 20. That's what this synthetic division can basically break down this cubic polynomial into for us. basically we just did this work to get this factored form of this cubic polynomial that we had a moment ago. All right, so this can't be factored anymore. However, this trinomial possibly can. Notice that they have a GCF of 5, so we should factor out the GCF. So if we do that, we have 5 out in front, then we have x minus 3/5. Go ahead and write it just like that. And then if we leave this one, we factor out the 5, we get x squared minus x, and then minus 4. Okay, so this is going to be that trinomial. So at this point, this is just a constant or coefficient. This is linear, not factorable, but we do have this trinomial here, and we should try to factor it. If you try to factor, it's not going to work. There's no factors of -4 that will add to get to -1. You can also check the discriminant here, and you'll see that it's going to be a non-perfect square. So you're going to have irrational zeros here. So we can't even use synthetic division just because that's only for rational zeros. Okay, so what we can do here is we can actually use the quadratic formula, and that will help us figure out what these zeros are going to be coming from for this trinomial. So doing that, let's see. All right, so let's see here. This is going to be x is equal to the opposite of b, which is going to be 1 plus or minus the square root of, and let's do b squared. That's going to be 1 minus 4 times a times c, so that's 1 and -4, and that's all going to be over 2a, right? So 2 times 1, which is going to be 2. Okay, so this is going to be 1 plus or minus, and then I think that's going to end up being 17, and that's going to be all over 2. Okay, so from here, what we see, we're going to have zeros, but we're going to get basically x is 1 plus the square root of 17 over 2. That's going to be one of our zeros, and then 1 minus the square root of 17 over 2. All right, so do we have all our zeros here? We could have had potentially up to 4. Let's see here. We do have one of the zeros, that's this one right here, from this -1/2. Another zero we just found out was this 3/5, right? So if we factor that, that's going to be this binomial of x minus 3/5. And then we just found out from this quadratic polynomial here that we have 2 more zeros. These are irrational though. So we have a rational one, another rational one, and then we have 2 irrational ones. So that makes 4 total zeros for this quartic polynomial. So in summary here, we have our zeros of x equals -1/2. X is going to be equal to 3/5. And then finally, we have these 2 irrational ones we came up with. So I'm going to say that's going to be x is equal to 1 plus root 17 over 2. And then x is equal to 1 minus root 17 over 2. So there you have 2 different practice problems where you practice using the rational roots theorem, finding zeros of these polynomials. We can do that by just looking for the rational ones here, right? So sometimes, yes, they're going to be irrational or imaginary and things like that. But in this case, we had all real zeros, which was kind of nice. The second one was definitely a level up in terms of difficulty. Anything higher than degree 3 will be definitely some more work because you have to use synthetic division more than once. So hopefully you found this video helpful. If you did, please consider giving it a thumbs up. And as always, keep up the great work, and I'll see you in the next one.